We have a process to auto vote for severity and detectability. And it may not work for all industries, but basically we take all the, let's say, detectability or severity, let's say all the severity effects that of an FMEA, and we put them into a list, and then we go through and we sort whether it's which ones are the most severe and which ones are the least severe. And when you do that, and then you go and let's say it's a scale of 1 to 10, then you go and you start putting in numbers. This is a 1. And now you've got an order and decide when you're going to differentiate between a 2 and a 3, a 3 and a 4. Once you've done that, you can then go back into this macro, and it goes and looks and sees what each effect is from a customer perspective for severity, and decides from its lookup table what that value is.
We really couldn't find any resources that talked about how to do software FMEAs. Mark did a great job at adapting the techniques and the processes we had with some help from me to bring this into the software world. And it is a fairly significant investment in time. So we do try to use it judiciously, particularly at the design or architecture stages in software where you can have the biggest effect. I had never heard of anybody using it prior to that. I don't know how many people outside of Teradyne are using it, and if you Google it, you still won't see a lot of hits. But I personally think that for anything that's mission critical, it's definitely the best technique that I know of to get ahead of the curve and try to anticipate what could go wrong.
Those are my guests, Teradyne's Mark Levin and Jon Bodin, next on Reliability Matters.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome, Mark and Jon, to the podcast. Thanks for being with me today.
Thanks for having us.
Thank you, Mike. Pleasure being here.
So, Mark, I found you first, and then you led me to Jon. Mark, you are the original, with your co-author, you're the original author of Improving Product Reliability Strategies and Implementations, published by Wiley, available on Amazon. And then at some point, you started working with Jon, and suddenly a second edition came out. And that book is entitled Improving Reliability, Product Reliability, and Software Quality. Strategies, Tools, Process, and Implementation, second edition. So before we get into the contents of the book and kind of get into the weeds on reliability, let's kind of talk about you guys for a little bit. Both of you work for Teradyne, not to be confused with Teledyne. I'm not sure how those two companies have a name so similar to each other. I'm sure you get that all the time. Mark, what type of products does Teledyne produce at your facility in Southern California?
So in Teradyne, we design and develop automated test equipment for electronics manufacturing industry. And that would be anything from, wafer level testing, package level testing, in-circuit testing, for the vast majority of electronic components. They could be memory, they could be microprocessors, basic power devices in automotive and cellular. And a lot of our products are designed to test high parallelism. So it's not unusual for a system, that's an automated test equipment to have anywhere from about 300,000 to well over 500,000 electronic components. So for us, product reliability is really important. And the other thing I want to say about, our equipment, the customers that buy our equipment, use it to test their integrated circuits and chips to make sure that they're reliable. And reliability is really important to them because every hour of downtime of one of our systems costs them anywhere from about 50,000 to 100,000 lost revenue and impacts their delivery commitments. So
no pressure on reliability, no pressure at all.
No pressure, especially when you consider the high complexity. Parts that have, close to 500,000 electronic components. if you ran like a MIL 217 or an Telcordia SR322 reliability model, you would get a very depressing number that would be totally unacceptable to our customers. And we tend to exceed that by close to an order of magnitude. So, the things that we do and that Ted and I originally developed, and Jon's kind of helped to take it to the next level when we brought in software quality, really allows us to be successful to meet our customer commitments for what their expectations are for product reliability.
Sure. I'm going to ask you some specific questions about your products, particularly when you mention automotive. That all these questions just jumped into my head. But before we do that, Jon, you're at the same company and Teradyne in Massachusetts. Does your division there build the same products, or is this a different type of manufacturing facility?
I used to be in the same division that Mark is in, and we have worked on some projects together. In the last couple of years, I've worked on a sister division. We also build testers that test components with a different kind of test, but that we test more or less the same components and have more or less the same customers.
And you mentioned you're testing components. Do you also test fully assembled assemblies with all the components on it, or is this a component level reliability endeavor?
The company actually does have a division which does board tests, but that's not the group that Mark and I are in. We are focused entirely on testing individual parts.
Let me ask you a question, a little bit of off script here, about, since you guys are component experts and reliability, QFNs, or bottom terminated components in general. What were people smoking when they thought it would be a good idea to mount a component right on the board with no clearance and no method of flux outgassing? Do component manufacturers live in a bubble and they come up with package requirements and function requirements, and assembly is left up to somebody else to figure out?
Yeah, that's a good question. I think with all these things, and we can get into this a little bit later, because there are components that the industry uses in high volume that Teradyne can't use because of the complexity of our boards. They tend to be large and stiff. Typical boards may be 130,000, so 30 layers of 1 and 2 ounce copper. So they're very rigid. But for all these package designs, and you could go back to the early IBM days when they had went from BGA to column grid to cast. All these things are evolutions. They get developed in, people find issues, and then it's up to the process engineers to figure out, can they live with it? Can they figure out ways to manage the risk? And we use QFNs extensively. We test all our boards for corrosion, and we don't have an issue with residue under the boards. And keep in mind that a lot of our products are doing very high frequency testing. So SIR, surface insulation resistance, is very critical. So if we had residue in there in between traces, it would affect electrical performance. So I think, it's a matter of, how do you be successful, having the right equipment, and making sure that you have the things in place to make sure that you understand the risk and that you've managed it and you can continue to control it, right?
Well, like so many other technologies, something new comes out and then it takes a year or 2 or 10 or months or weeks, whatever. It takes a period of time for the users of those new technologies to get a handle on how to, what best practices are, what tips and tricks and black magic and technology can be combined to successfully integrate that new technology into production. Almost all new technologies come with some degree of a learning curve. I think in our industry, plug and play is something we strive for our customers, but the process of building a plug and play device has very little to do with plug and play. It has a lot to do with learning the new device and learning how the device likes to be mounted to the board, what types of clearances, whether the solder mask around the board needs to be modified or increased or decreased, et cetera. And I'm talking about the contamination part of the process in assembly, not so much other processes. I look at the world, they say, Maslow said, if all you have is a hammer, the whole world looks like a bed of nails. In my case, I'm a cleaning guy, so I look at everything being dirty and how do I make it cleaner. So if we had our way, every component would have an inch of clearance under it so that we could scrub everything out. But of course, if I had my way, cell phones would be the size of automobiles, and automobiles would be the size of buildings. And so I can't get that.
To put it in perspective, Mike, I remember when I first started at Teradyne, one of the first projects I worked on, this is going back maybe 24, 25 years, Teradyne was just starting to get into BGAs, and they could place them on the board, but they couldn't rework them. And this was in the early days of rework equipment when Airback was just coming on board. And, you could make that same argument. What were they thinking when it came to these BGAs, these high bolt counts? And, the probability of doing the rework reliably was really difficult. And, back then we worked with Airback on, trying to perfect the reflow profiles. We came up with a method of using feedback where we sensed the bottom side temperature and modeled with the temperature differences, so we knew when it was getting to liquidus. And nowadays, everyone does BGA rework with very high yields and very low defect rates. So when you look at things like QFN, all these things go through an evolution. They come in, engineers identify the problems, and the one thing engineers are good at is that finding solutions, at fixing problems. And it's just a matter of the maturity. And just to put it in today's perspectives, a lot of the drive in electronics going forward, it's all in high frequency, millimeter wave. And a lot of these components are coming out are in new packages to meet these higher frequency needs. A lot of them haven't been tested. And so, this never ends. And this is why the field of reliability is such an exciting field, because there's always these challenges.
Yeah, we can translate that to job security. I think the combination of high frequencies and IoT and automotive dragging these technologies into harsh environments is certainly a perfect storm of reliability challenges. Is that right?
Yeah, in automotive, it's higher and higher power, higher and higher voltage.
Right.
Solar, all these things keep on driving new challenges.
I'm reading that the new automotive low voltage, particularly on electric cars, is 48 volts, and the new automotive high voltage is upwards of 1,000, and they're even talking about higher voltages. Everything has to be perfect when you're running 1,000 volts through a circuit board. There can't be anything ionic. There can't be anything debris oriented. There can't be anything that could even remotely result in electrochemical migration effect or other effects that affect the frequency. We are definitely, I've said this in other episodes, we seem today to be at the edge of an envelope. And normally when we're at the edge of the envelope, like Mark, you mentioned BGAs. We were at the edge of the envelope with BGAs. Everyone was complaining that, how can we rework these things? What were they thinking? We were at the edge of the envelope, and then eventually the envelope gets bigger. And then, BGAs are now kind of the center of the envelope. And now QFNs and other bottom terminated components are at the edge of the envelope. And it's, we're just waiting for the envelope to get bigger, because we're definitely producing products that are edge of envelope, going into very harsh environments with very high voltages, very high frequencies, with very high reliability expectations and even higher costs of failure. And I cite the automotive industry. BMW just a few months ago recalled some of their iCars, some of their electric cars. They did a full model year recall on it. And they stated that the reason they had to recall it is some of the boards turned out not to be cleaned properly by their tier 2 supplier. So I imagine they now have a new tier 2 supplier, and they fixed that. But certainly when we take products and push their reliability expectations due to the nature of what they do, and we build them with smaller and smaller parts with higher and higher frequencies and put them closer and closer together, you guys have enough work to last you 1,000 years.
Yeah, but it's more complicated than that. That whole supply chain management is, in fact, we talk about a little bit in the book, is a critical part, because you could even have a good supplier, but then, you got to keep on going further and further back to the raw materials. So controlling things like counterfeit materials. So, even supplier management, having quality suppliers can still be problematic. And the things are, what tools and processes do you have in place define these things when they do surface, or do you wait till the customer finds it for you and then it's too late and very costly?
And we're doing a webinar next week. By the time this airs, this will already have happened. It's called SMT Wars for those who want to look it up on our website. And to your point, Mark, about finding quality suppliers, this particular manufacturer had an issue with conductive anodic filament CAF issues, and it went back to the supplier. It went back to the choice of materials. It went back to the drilling processes. It went back to all sorts of material selection and assembly practices, not best practices, just practices that led to this catastrophic event with 50,000 units recalled. So you're right. It definitely, the problem is not fixed at the symptom level. The problem is fixed at the origin. It's fixed at the cause, which is usually quite a bit back in the food chain.
So I'll share with you a story. You talked about CAF. Many, many years ago, we started seeing some CAF failures in circuit boards. And keep in mind, our circuit boards are typically 16 by 20 and, 1/8 of an inch thick. And finding that reason for the CAF is kind of like the needle in the haystack. And we've worked with Cal University of Maryland a lot. And we found that the defect in the board, it was cavasol, large particles that allowed for the CAF to grow. And when we peeled the onion, we found out that there's only a couple of manufacturers that were making cavasol for board fab, and this was the major one for the electronics industry. They had developed a hole in their filter, and larger particles were getting out at some small rate and were causing these CAF failures. So even quality suppliers, if not well managed and good controls, can be can have these issues pop up.
Absolutely. Now, Jon, your world has got to be so much easier, and I say that kind of tongue-in-cheek, than Mark's, because Mark has to deal with an infinite quantity of materials. In your world, as a software engineer, you only have to deal with two, ones and zeros. Right? At the end of the day, you're dealing with ones and zeros, and so you only have
typical hardware engineer kind of comment.
Exactly. I get it. Yeah, but how difficult could two numbers be? But in your world, to be serious now, in many cases, it's certainly much more difficult than maybe mechanical reliability, because on a mechanical reliability, the problem can be reproduced more easily than in software. Software is mysterious, and software is tricky, and software involves predicting the future, much like other reliability issues. But software requires you think way, way, way outside the box, because in our experience, which is much simpler than yours, in our equipment, we write code for our equipment, and we could have our equipment out for 5 or 6 years, and then suddenly we get this crash, and we don't understand why. And again, as a mechanical person, we'll completely understate software. Is the problem with software is it does exactly what you tell it to do. If you don't want it to do something, don't tell it to do it. But it certainly in our world, we didn't think someone would press this button while doing this, while doing that, while wearing orange socks and a baseball hat. And that combination of events, which was unforeseen when the code was written, crashes the program or causes something to happen that's undesirable. In your world, as a senior software engineering manager, what types of classic failure mechanisms, if there is a classic failure mechanism, do you look for, and what are the really tricky ones that you find in front of you from time to time?
So there's a large range of things, and it depends on what particular piece of code, kind of code you're looking at. These days we have long checklists. We look at hardware that doesn't function correctly or unusually. We look at user inputs that might change. We look at security kind of issues. It's a very broad range of stuff. And you do your best to try to anticipate every unusual thing that could possibly happen and take into account that and write code to handle it. And then, of course, you also are just going to have regular old errors that are going to sneak in that you have to deal with as well. One of the things that we've done here at Teradyne a few years ago is started doing sort of traditional FMEA analysis on software to try to anticipate some of the things that could happen that you might not otherwise think about. And that's been kind of an interesting technique for us to use here. But lately in the news a lot, you hear a lot about security breaches and exploits. So that's something that we've also started to spend a lot more time in the industry thinking about recently, that even 10 years ago wasn't such a big deal. But now that everybody realizes how many bad actors there are out there, you have to really spend a lot of time thinking about how you prevent your software from being exploited.
Do you guys write like raw code that lives directly in a chip, or are you relying on an operating system of some sort, whether it's Linux or Microsoft or whatever, or ladder logic from a PLC? Is there a particular type of software that you are used to working on that relies on a larger OS, or is this something that you control completely?
There's a very broad range of software that we put into our products. Everything from, at the lowest level, we do have groups that write logic that go into FPGAs. We have embedded software, some that is at the device driver level, some that runs embedded Linux, embedded Windows. There's application code. There's code that deals with back-end logic. There's code that has user interfaces. So if you looked across the board at stuff we do, I would say the answer is, yeah, we do everything.
Yeah, that makes sense. In our world, we write code that lives on a Microsoft operating system. And Microsoft is notorious when they come out with a new operating system, you generally stay away from it. It used to be said, back in the 70s and 80s, never buy a first-year General Motors product because they take the first year or two to fix the bugs. And obviously, it's much better
we say
today.
That too. Never deploy a 1.0 product.
Exactly.
So.
Buy at least the 1.1 or maybe even 1.01, but at least wait for a round or two of upgrades. And that's come to bite us. We were on XP for a long time. We went to 7. We skipped 8. There was no 9. And now we're just starting to deploy 10. And we even had in our little world, because we don't have this economy of scale that your company has, we build many hundreds of products a year, maybe 1,000 products a year altogether. And so we don't have this economy of scale. So when even a service pack comes down, we have to prevent our equipment from auto updating because Service Pack breaks things. And, because we're not like in the circle, Microsoft circle, when they are beta testing various versions of software, we find out when the public finds out that it's broken. So we tend to be very cautious at embracing new updates to operating systems or service packs or things like that. That's our smaller world. I know that probably affects you guys. Only you guys, maybe because of who you are, have a closer to a seat at the table when these patches and updates and service packs and new OS versions come out. Maybe you're already prepared.
Well,
for that.
we really have to deal with all the same issues as you do, and we pretty much try to lock down as much as possible. Lock down the versions of software, turn off auto updating and such in production. Our customers are very leery of pushing anything new down.
Yeah.
So we have customers that are running the old code. I mean, we have customers running on things on Solaris and stuff that was, built 15, 20 years ago. And their attitude is, if it ain't broke, don't change it.
That's our attitude too.
It's a fine line because particularly with these days, just going back to the security for a minute, every day you're reading about new exploits and so there's a fine line between a major upgrade, Windows 7 to Windows 10, versus we really need to deploy a patch that plugs some potential hole.
Right.
In many cases, our customers are running, on isolated networks and behind firewalls. So, there isn't quite the same sense of urgency, but it's, but they don't necessarily trust their everything is breachable. So, you have to kind of get on a cadence of testing new patches and then rolling them out to the field in a very orderly fashion. But we do try to control that quite a bit. Even a patch can change the performance of a product, and if you're running high performance products, it could change how long a test takes to run. If a test takes longer, that cuts into our customers' products, their profit, because test time is expensive. It could change other behaviors. So we tend to control that in the field, and partly it's driven by customer needs. If they're concerned about things, and we try to stay ahead of that.
It's a classic risk-reward calculation there, whether it's riskier to roll out a new patch and face equipment issues, software issues, or keep it stable but risk a vulnerability, a security vulnerability. I guess that's always the calculation these days. And Jon, you did give me great comfort to hear that that you have the same experiences we do. So it's nice to hear that a company many times our size. I'm glad to hear that. Sometimes we live in a bubble and we just think, why us? Why is this happening to us? But it's nice to know. Yeah, misery loves company. So thanks for the company. Let's talk about the book.
So glad to help.
Anytime I feel bad, I'll give you a call, Jon. So let's talk about the book. Mark, you and is it Ted Kalal? Is that how he pronounces his name?
Yeah, Ted Kalal.
Ted Kalal. You and Ted Kalal co-authored the first version of the book, which was not including software. Tell me what the motivation was to at first publish that book, and then I'm going to ask you the same question about the second edition where software was brought into it. What made you sit in front of a computer for months or years or however long it took to take the knowledge that's in your head and memorialize it on paper?
It was certainly years, and it's a good question. What drove the book was back in around 2000, Teradyne's reliability function was decentralized. They had reliability managers in each different division. All the reliability managers were really smart people that were moved from one position and said, you're now a reliability engineer. And the reliability performance of our systems were not meeting our customer needs. And so we're getting ready to start a new platform, and they wanted to do something different. So they brought in Ted Kalal from the outside. Ted had experience doing HALTs, and they knew that that was one of the things they wanted to do. But they really wanted to revamp the whole reliability program. And so I moved over from DFM, from operations, and I'd been starting to study reliability. So Ted and I were kind of tasked to create a new process. We started out by bringing in Dr. Michael Peck from Cal University of Maryland, spent some time here talking about physics of failure. And we brought some other consultants. We looked what other people were doing in the industry. We read lots and lots of books. And, we created this reliability process that we implemented. We created a reliability lab at our facility. But the one thing that we were surprised is there was no source that we could go to that talked about, why you need to do this. How do you implement a reliability program? What are the parts that you need? Why people try it and fail? What are the barriers? And what are the tools and processes that need to take place? So after we had launched this reliability program, we started to have really good success. Our reliability within a very short time period had over doubled. And if you look back from that time period when we first launched it, it's increased by over an order of magnitude. So the real motivation back then was that we wanted to create a book that kind of someone could pick up that's not a reliability engineer. Keep in mind that a lot of the reliability books are very technical. They're very mathematical based, and they're really geared just for the reliability engineer. But if you're a manager, if you're a business owner, and you want to implement a reliability process that's different than what you're doing, there's no real tool, there's no resource that you can go to that says, these are the things you need to think about. These are the decisions you have to make. These are the reasons why people that keep on trying it time and time again aren't successful. And so that was the whole motivation for the original book, was to kind of get something out there that we thought there was a real need for in the industry.
So it's not a reliability book written specifically for reliability engineers. It's a reliability book written for reliability engineers and managers and other people to help guide them into the bowels of reliability. Is that a good, maybe not the word bowels, but
That's true.
Is that a good way to put it?
Yeah, but universities do use it as a source for teaching reliability engineers about reliability management. And so I know University of Maryland was using, I don't know if they're still using it, but they had a summer program for their graduate program reliability where, the book was kind of the source for, what are the tools, what are the processes, how do you implement it? So it was geared to, for anyone to understand. In fact, my wife, who's non-technical, did the first edit. And one of the feedbacks was if she could understand it, then I felt we were reaching the right audience, that, we weren't trying to be heavily mathematical in our analysis. We're trying to give people tools and techniques that are practical. And if you think about in the old days when we used to talk about TQM and quality, quality is everyone's job. In a lot of ways, it's no different for reliability. Everyone's responsible for developing reliable products. So if we put this out there in very highly mathematical and statistical tools, that people aren't going to grasp it. They're not going to be able to use it. And so we wanted to put it out there in a way that everyone could understand and could act on it.
I think Fred Scheckelberg, the reliability expert, uses your book in teaching at the University of Maryland, if I'm
That's correct.
Yeah, he was a guest on the podcast a few months ago. Interesting person. So that was the first book. What was the motivation to the process of writing a book can be quite exhausting, and what made you jump back into the pool again and come up with the second edition?
And so about 5 years ago, we were getting ready to start a new platform, which meant new software architecture and, a typical system in our AT equipment is going to have many millions of lines of code. And so we were starting to implement CMMI for software quality. But one of the things they wanted to do was to do a software FMEA. And at the time, Jon was actually managing the software side of it. And so that's how Jon and I became friends and started to meet. Jon and I were kind of tasked with, I was going to take my FMEA process and apply it to software. And one of the things I found when I started doing the research again, because one of the things we always do when we develop these things is we develop training. We go out and we train people. So before they actually start to do it, they understand what it is they're doing and how to do it. We take them through a simplified example, whether it's a hardware example or software example. And so we worked with some consultants. I didn't see a lot of material out there that talked about software FMEA. So I started to see this need. And the other thing that we were seeing was there was this transition where in the early days, everything was around hardware reliability. But software was taking a bigger role in products of the future. And it continues to be. And you can just look at the automobile from the early days when it was all mechanical. So when they started having electrical things like electrical windows and time-delayed windshield wipers. So when they start putting in, little computers like for the radio and things like that. Nowadays with AI and self-driving cars, it's completely changed. And so the other thing that we were seeing was that the industry was shifting, that there was more and more firmware and software that was being embedded in products, along with security. People were going out there and doing pushes on the web. And we felt that this really required a change in the way companies look at how they're staffed and the skill level. And so part of the motivation of the book was to kind of revamp hardware reliability to be hardware reliability and software quality. Talk about, the two, how this paradigm is shifting, how the skill set's shifting. And then the other big driving force was the fact that hardware engineers and software engineers are very different. They in essence, speak different languages. Hardware engineers look at problems very differently than software engineers. Software engineers think of product release in tiers. We'll do tier one, we'll make sure at least the minimum set is working. Where a hardware engineer kind of strives to have perfect products. They write requirements that can be fully tested. And so hardware engineers and software engineers, by nature, because they speak different languages, weren't interacting really well. And we wanted to kind of pull in that requirements and how in these complex product developments, not just what are the hardware tools you need and software tools, but what are the things that you need to consider for them to interact and to be successful. And so the other part was really pulling in the software quality.
Right, and now you started to have a lot of hardware managers that found themselves managing software projects as part of their deliverables and really didn't have the background or the tool set to do that.
I would think a hardware manager managing software is a fox in the henhouse scenario where not too many good things can come out of that from a software perspective. Is that right, Jon?
If they have an open mind and they are willing to understand what's involved, then it can work out okay. I'll put it this way: every hardware company I've ever worked for, it's always hardware managers that are the senior managers. So you get used to that after a while.
Well, I guess hardware is what the customers see first. Software is inside. Software is what you don't see. It's like that Intel Inside promotion that you see when they advertise computers. It's a way to try and raise awareness that it's not just a metal box with flashing lights. There's something inside. There's a brain inside that
without
makes it work.
all that beautiful hardware you can build without any software, it really doesn't do anything.
There you go. There's that software engineer talk. I love to hear it. So the first book had a section on failure modes and effects analysis, FMEA. The second book has an entire chapter. Is the difference the inclusion of software, or has much changed between in the FMEA world from the first book to the second book?
Well, certainly the inclusion of software was a huge motivation, addressing how you do software FMEAs and software fault trees and how they're different, and ways to approach it. But the other was, when we first implemented FMEAs at Teradyne, they took about a week to do about 40 hours as we put in the project. Nowadays, we do FMEAs typically around 8 to 9 hours, 3-hour meetings. We try to keep the meetings no longer than 3 hours because we find that an FMEA is a mentally tasking project to begin with. Forcing engineers to deal with very complex designs and not think of it from how they function, but how they can fail, and it's mentally draining. We started implementing things that could improve the brainstorming process and simplify the logistics. And most companies use an Excel spreadsheet to do FMEAs. Teradyne's no different. And over the years from when we launched this, we kept on implementing improvements to the tool. Some of the things that we came up with was auto voting. We have a process to auto vote for severity and detectability. And it may not work for all industries, but basically we take all the, let's say, detectability or severity, let's say all the severity of effects that of an FMEA, and we put them into a list, and then we go through and we sort whether it's which ones are the most severe and which ones are the least severe. And when you do that, and then you go and let's say it's a scale of 1 to 10. Then you go and you start putting in numbers. This is a 1. Now you've got them ordered. You decide when you're going to differentiate between a 2 and a 3, a 3 and a 4. Once you've done that, you can then go back into this macro, and it goes and looks and sees what each effect is from a customer perspective for severity, and decides from its lookup table what that value is. And it solves things from like creep. If you have large FMEA spreadsheets, it's not uncommon that you could have the same effect or from a customer perspective and give it different weighting values, because as you go down, either people become more sensitive or less sensitive. So we've kind of created this auto voting. We came up with another technique where we put Y's and N's in there. And what a Y is, let's say in the initial phase you're brainstorming. You just want people to give ideas. And then you start going in and you start filling in the rest of the FMEA. And you may come up with something and an engineer says, that needs to be fixed, right? That's unacceptable. And so we'll go into any of the blocks for severity, the RPN, whether it's severity, detection, or probability occurrence. We'll put a letter Y in there. What that means is yes. And so it now grays out everything. We just stop talking about it. if we've agreed that we're going to fix it, let's not spend any more time laboring over the value of it, right? We've decided. Same thing with an end. There may be things that come up and you decide that this could never happen, or that, someone comes in and says, well, the design changed. It doesn't behave like that anymore. And so we'll just put an end in there. And that basically says we're not going to spend any more time on this. The same thing with the thing we do when you're doing failure modes and failure causes. A lot of times, every time you do another failure mode, you may have to create a new row. Or if you have a failure mode and you got 6 different causes and you've only got 4 rows in there, you have to start inserting rows. And so we came up with this method called pipelines, where after each, let's say, failure cause, you put a pipeline. And then so the team is looking at all the different causes that could occur, and you put it in a single cell. And then you just run a macro, and that macro now creates a row for each one of those. And so it helps you to minimize the time you're spending managing the spreadsheet and maximizing the time where you're trying to keep people creative. Because every time you put someone on hold because you have to insert rows or do some kind of Excel logistics, it kind of kills the creativity.
Stops
puts
the
people
momentum.
back on the back burner.
Right.
The other thing we did was creating the parking lot. And that's probably one of the biggest things. A lot of times, in fact, I don't think I've ever been in an FMEA where something comes up that's really important, but it's not relevant or germane to what we're doing on, what we're working on. It could be a different design. It could be a manufacturing process issue that people realize that this needs to be solved because, you've got this cross-functional team and something comes up and he says, we need to figure out how we're going to either manage the manufacturing or it could be a supplier issue. And so what we do is we create this parking lot where we basically move these things into the parking lot so we don't spend any more time on it. So one of the biggest things around FMEAs, and we're still continually looking at ways to make improvements, is how can you maximize the efficiency and the effectiveness of the FMEA. And so because of that, we've dedicated a whole chapter to that because it is a big subject. And if you look at the reliability tools that engineers have, probably the FMEA is the biggest tool that they have for improving, design. And I say that because you find lots of things, some that may be real, some that aren't, right? But making those decisions early on when you're at the architecture phase or before you've gone to first prototype are much easier to do than when you're, at DV and you find them, right? Where now you're going to the software guy and saying, can you fix this with a patch or do a software change? So, we are doing more and more software FMEAs because of it. We've seen the FMEAs are really effective. We do user application FMEAs. How can a user use the product in a way we hadn't intended? We do process FMEAs. We put a whole section there around process FMEAs. How can you design it right and build it wrong? So we felt that FMEAs were so important, and we had, at this point, close to 20 years experience that we need to kind of put some more meat into the FMEA and give more tools to people to be successful.
Yeah, so Mike, earlier you asked about how do you anticipate with software what people could do or what could go wrong and whose crystal ball is really that good. I think bringing the FMEAs to software is the biggest single step that I've taken to help get ahead of that curve and really try to identify the areas that could be problems and decide which one's really serious and what you should go take care of. The rest of the kind of techniques we use, like RCA, are all backwards looking.
Right. And this is forward looking. So, Jon, in your world of software engineering, is FMEA kind of a new concept, new for you, new for your company? Is this something that is less common in the software development world as it is in the hardware development world?
Yeah, absolutely. When, as Mark said, we started this project about 6 years ago, and my group was working on core architecture, and I went to Mark and I said, I think we should try doing FMEAs on this. And at that time, we really couldn't find any resources that talked about how to do software FMEAs. Mark did a great job at adapting the techniques and the processes we had with some help from me to bring this into the software world, and it is a fairly significant investment in time. So we do try to use it judiciously, particularly at the design or architecture stages in software where you can have the biggest effect. I had never heard of anybody using it prior to that. I don't know how many people outside of Teradyne are using it, and if you Google it, you still won't see a lot of hits. But I personally think that for anything that's mission critical, it's definitely the best technique that I know of to get ahead of the curve and try to anticipate what could go wrong.
So you don't have to give away any company secrets here, but I'm just thinking two scenarios happen when you approach your team and say, okay, we're going to bring in FMEA for software. They either go, yes, that we were waiting for that. Why didn't we think of it sooner? Or they go, are you kidding me? We don't need to do this. We're software people. That's their job. We don't do that. Was it embraced?
Or they say, what's an FMEA?
Yes, exactly. Maybe they come up with their own acronyms, and I can almost guess what at least one of the letters are. So is that something that had to be learned and had to be kind of push through to get acceptance, or was it pretty?
We have, to some degree, yes. We have, when I was first came at Teradyne, and I was very involved in getting us to CMMI level 3, and we did a lot of process re-engineering. And the people don't like change, so there's a lot of pushback. And what I always tried to do was say, hey, this isn't me imposing process on you. This is our process for how we get better at what we do and how we build better product. And I think that some of the culture that's really good here, and things I've always tried to convey to everybody is, you participate in this, and whatever these tools are, whether they're other procedures or whether there's things like FMEAs, they're tools that help us do a better job. And if they're not working for us, we change them. So people have generally, by the time we started trying to do FMEAs for software, we already had a pretty accepting culture about trying out new things. And now, there was still some pushback. People are conservative and don't like change. But I think that, using it judiciously, I think the people that were involved in the initial FMEAs definitely saw the value. Once they've gone through the process, see how, it helps them do better design and architecture. I'm about to introduce FMEAs to the group I'm in now. There'll be pushback, but they'll go through it. No, once they see, oh yeah, I never thought about that. It's a good thing we did this process.
Right.
They typically come around.
But the Teradyne methodology is we always roll out training first. And so when John and I were doing this, I created this FMEA around the tire pressure monitoring system, TPMS, and it was kind of nice because we could pull in hardware engineers, software engineers. We take them through the whole software process, the hardware process, the interface process. And then we do at each of the stages, whether we're doing full trees or filling out the FMEA form, we take an example where you have a low tire pressure and that the end user isn't warned. And, it's interesting when you try, have the software team work together, hardware team work together, and then maybe a cross-functional team, some hardware and software guys that try and approach the problem separately, looking at the interface, the things they come up with. And, it's probably one of the great examples because it's something everyone can understand. Everyone knows how these tire pressure monitoring systems work, how they report to the computer what the pressure is. But you could envision, as we give them all the tools, we give them the building blocks, we show them the design for a tire pressure monitoring system, how you could actually have, a low tire pressure and not know. In fact, in the first time I think we rolled it out, I think John was there, someone came up with the idea that, we did this in Boston, we did the first training, and there people have snow tires, and when the winter's over, they change their tires, and someone came up with the idea, well, what if you had your tires in the back of your pickup truck and you didn't reset it, so it didn't know that you had new tires on there that it should be monitoring. And it turned out that was a real problem. And, the thing with the TPMS is that it had an accelerometer in there. So we used that as an example, saying, you could have found this in the FMEA, and then you could have, in your design, said, well, if the tire, if I'm rolling and two of the tires aren't moving, if I'm not picking up any acceleration, I know that there's a fault mode. I'll send a warning to the end user that you need to go in for service or something wrong with the tire pressure monitoring system.
And that's a good example of combining a hardware and a software fix for that. The accelerometer being the hardware and the software saying something's not spinning, something's wrong here.
So I think the real key in all this, if you're rolling out software FMEAs to an organization that hasn't done it, you have to develop the training. You have to basically bring them in. It's like a 3-hour training class where they each do the examples. Then we get together as a group and they talk about the things that they found. And then they walk away with the discovery of, I feel comfortable. I know how this works. I use it on something that's still complex, but I can now apply it to my product.
Sure. I have about a dozen more questions, but we are running out of time. So I'm going to bring it down to 2 more questions. The first question I'll have each of you answer, Mark and Jon. What do you see as the biggest reliability challenges facing our electronic assembly industry as we move forward?
Yeah, for me, things continue to get more and more complex. And the whole motivation of this book was around software. When I first got into reliability, everything we did was hardware reliability. And I see software, firmware, software security, the Internet of Things, all these things are driving new challenges in the world of reliability. And also the complexity of systems, with automotive and self-driving cars, really driving the need to in some ways, the reliability to mess up their game because the risks are getting greater and the complexity is changing significantly. And so I think that's the big challenges these days. I know University of Maryland teaches a lot like prognostics, PHM. We used to look at reliability as, you bring it in, you do preventive maintenance, and then we started using like miners to look at things. But, with prognostics, we're starting to think about, are there sensors and things we can embed that are constantly real-time monitoring and sending us how things are behaving? Because things don't go from a good state to a bad state instantaneously. In most cases, unless there's electrical overstress, unless you actually stress beyond its use, it goes through a degradation period. And so that's a complex thought for a lot of reliability engineers. How do I create systems that can be PHM type, where we're actually monitoring the health of the system?
Very good. And Jon, what's the biggest reliability challenge facing the software industry as we go forward in time?
Well, certainly, as Mark said, the complexity of the systems. I think in like the 40 years I've been in the industry, one of the major changes is just how much software is now in life controlling or mission critical types of applications, and plus the fact that everything is now interconnected and online. So, 30 years ago, 40 years ago, if your program crashed, okay, maybe you had to go and retype that document or enter some more data again or whatever, run that analysis again. Now, your program crashes and your car crashes into a telephone pole, or your heart rate monitor, your pacemaker stops and someone dies. So the systems are more complex. The technology is moving really fast. It's hard to keep up. Hardware is definitely ahead of software. And there's just much more to consider all the time. So I think that trying to understand how things can go on in a much more interconnected, much more complex systems is really the big.
Yeah. It's a part of it. I think the challenge is cultural. When new technologies first started appearing in cars in the last 20 years, lane, not lane warning departure, but the blind spot indicator. It was really at first received as a convenience. You still checked your mirrors, but you checked your mirrors to see if the warning indicator was accurate. And when I first purchased a car that had those safety features in it, lane departure warnings and blind spot indicators and things like that, it would only be a convenience for me. I still had the old habits of turning over my shoulder and looking in my mirrors and things like that. And then as my second and third car started having those same features, it now has become a primary safety feature. So even though it was introduced a little bit more as a novelty and a convenience, it's now relied upon. So these technologies can't fail. And we always have the ability to, in that same example, to look over our shoulder and make sure the lane is clear. We don't do that now because we rely on the technology. And so,
well, and even more so. I mean, you have cars now. They know how the car in front of you stops suddenly. Your car stops suddenly, even
Yes.
if you're fiddling with the radio. That kind of stuff saves lives, and those weren't technologies that even existed a few years ago.
Sure.
And if those don't work, you rear end somebody.
Right. We are now relying on these innovations, which went from novelty stage to basic safety, and not only do they have to work when an object is in front of you, they cannot slam on the brakes when an object is not in front of you. They can't fail that way either. So there can't be any false positives because that can also cause some serious safety issues. So yeah, the stakes are very high today in all sorts of electronic assembly applications. My last question is, as a reliability engineer, you're responsible for predicting the future and determining if a product really is shippable that day or that season. Back in the 70s, when the Japanese were producing cars, Toyotas and Datsuns, as they were called back then, that was a real challenge for the American automobile industry because we were still building big cars, and the car quality in the 70s was probably about the worst it ever was in the American automobile manufacturing days. And I remember Lee Iacocca, famously purchased either a Honda or a Toyota, I forget which one, and brought it and put into the country and put it in Detroit, put it in the factory and said, this is what our competition is. This is what they build. These are good cars. And we need to match that. And I remember reading that he supposedly, this may have just been a press release by their advertising people, but it was interesting to hear. They claimed that any worker on the assembly line could basically push the stop button and stop the line if they thought there was a major quality issue coming down the line. Now, I don't know if that was advertising hype or not. I would guess if it was true, I would wonder if that person's still working there the next day, because that's a major thing to shut down an assembly line in the automotive industry. But with that in mind, and as a reliability engineer, do people tend to shoot the messenger? Or I'm not talking specifically your company. I just mean in general, your general experience as you commiserate with other reliability engineers in the industry. Are you guys internal affairs of police, where they're hated and needed at the same time? Or do people understand what you do, and do they see a bigger picture today versus maybe 20 years ago?
Yes. So I always say reliability isn't a policing function. If it is, you've already set yourself up for failure. And we can take the quality example, or we could take the reliability example. In both cases, it really goes back to the culture. So if you take the quality example, if you had a corporate culture of quality is number one, right? And the Japanese were building high quality cars, and that was the culture back then, and they were committed. And there, when you basically put that red light on, you stopped it. They're looking at as an opportunity to continue to find an issue quickly. It's supposed to focus all your resources to quickly address a real issue, right, or a customer issue, and get the line back up and running. The same thing goes with reliability. You need to instill a culture for reliability, right, and it's got to start from senior management. If senior management does not buy into the process, then what you're talking about happens, right? And it's just an activity. But when management is committed to reliability, that culture now, if implemented properly by the reliability engineers, comes to corporate culture. And you have engineers that if something comes up, they'll say, Mark's not going to like that. We can't do that. Or they'll call me to find out, can we do this? So when you talk about, raising the red flag to a reliability issue, companies that are committed to reliability, that have seen the impact of letting something go by. And the reality is, whether it's a quality issue, whether it's a reliability issue, if these are significant, they will come back. And it will cost you much, much more in the end run. And it also affects your brand equity. It affects your reputation. So it's not just a monetary cost, there's the intangible cost. So companies that are really committed to it don't look at it like you threw the switch and now we can't build anything. They look at it, we need to get everyone down there to figure out why this is happening, get it resolved quickly so we can get back online. And so to me, it's really the culture. And people that look at it like, Johnny just stopped production, now we all don't have jobs. Probably in that environment didn't really create a quality culture, right? They weren't committed. It was more lip service.
Well, at that point, you create a cat and mouse culture, right? I love your comment. I think that's the takeaway of this particular episode, which is reliability is not a policing matter. It really is a cultural matter. And if your culture is to build a fine product, then reliability engineers are a strong tool in delivering that fine product. If the culture is how quickly can we build it and what can we get away with and how much profit can we make, then reliability engineers are people in the way of the goal, which is not to build a quality product, but to just make some quick money. So that's a great way to end this episode. Thank you both, Mark and Jon, for being my guest today on this episode of Reliability Matters. If people are interested in the book, I found it on Amazon. Is that the best way to get it?
Yeah, I think that's probably the easiest way. Amazon. If you just Google, or not Google, if you go on Amazon, you just start typing in improving product reliability, the book will come up.
Yeah, that's how I searched it. I didn't even give it the subtitle. I just put improving product reliability. It was the first one that popped up, both the first and the second. And I would recommend the second because the second encompasses most of the first and adds quite a bit more material. So great read and really good material. And thank you both for your insight and for your knowledge of reliability matters on the Reliability Matters podcast. I appreciate you both being with me today.
Well, thank you for the opportunity to talk to your audience.
Okay, thank you very much for having us.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on iTunes, Spotify, iHeartRadio, or wherever you get your podcast. Reliability Matters and other reliability-based podcasts are available at Circuit Assembly's PCB Chat at pcbchat.com and at Ascendo Reliability at reliability.fm. Thanks for your comments. Please keep them coming. Send comments and episode suggestions to Mike at mikeconrad.com. That's Conrad with a K. Until next time, thanks for listening and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.